So what we're trying to do here is find an equation for a polynomial. Okay. And Nicholas, how did you start this?
I started by picturing the function as if there was no let's say a negative 4, 1%. So say if you added 4 to the entire function.
So if we take this same function, Nicholas suggests taking the same function, which I'm tracing now somewhat poorly in blue, and kind of shifting it up by 4.
You have 3 new intercepts. One is at -3.
So new intercepts at x equals -3, 0, right, and 2. Is that correct?
Yeah.
All right. So Nicholas, why is this helpful? I mean, what are you going to do with this information?
I mean, just based off the intercepts, you can write out x plus 3. I mean, you're trying to think about the zero product property.
I like it, thinking about the zero product property. So we know the factors would have to be x plus 3.
X multiplied by x.
X.
And x minus 2.
And x minus 2.
Can I interject with a quick question?
So, yes, please interject.
Okay, computer. Since, that's an album, by the way. Since this, like, the graph's all wonky, why is there one unified equation? I never really understood that.
Why is there one unified equation?
Like, obviously it follows different patterns over different ranges.
Right. But there's one unifying equation because basically we're just defining the fact, right, if I'm not mistaken, there are like 3 zeros, right? We know there are 3 zeros to the function. So this makes the function 0 at those points because of the zero product property. And the behavior intermittently is just, that is a result of just the function.
So it's not like a way to represent a few functions, it's actually just one function?
This is one function. Yeah.
It's not piecewise.
It's not a piecewise, it's just one function. Okay,
Wow.
So Nicholas has gotten us to this point, and now I'm going to pass the hat. Unless there's a question.
I have one other thing. I'm not sure
One other
how
thing.
it works, but
One other thing.
Since the actual function is 4 down,
Right.
4 down the y-axis, you can write -4 at the end of it.
Right, so Nick is reminding us that to eventually get back to our original function, we will need to subtract, like eventually we will need -4, right?
Right.
So we'll have some function, and then we'll we'll have some mess here, and then it'll be like -4, correct? Okay, good. So, we return to that. Next step, Mackenzie.
So you see where x is 0?
I see 3 places. Oh, no, I see one place where x is 0.
0.
No, yeah, you were right. One place where x is 0. Okay. Go on.
That's in the shape of a cubic function, so that's going to be a triple 0.
Because this is in the shape of a cubic function, it tells us that the 0 here is a triple 0, as Mackenzie says. So what does that mean?
So it means it's x cubed.
So that means that not only do we have a 0 at x, we actually have 3 there, or the idea being, right, this, or like x times x times x, right? So y equals x plus 3 times x times x times x times x minus 2, or just y equals x plus 3 times x cubed times x minus 2. Great. All right. Beautiful. The next. Well, what might a good next step be? And there are a couple different ways to go about this. Caitlin, yeah.
Okay. Now that we've figured out where all of our x's are, we want to solve the equation for a, which is not here yet.
So a is what?
So
Yeah. What is this a? When you say solve for a, I mean what is that a?
Oh, it's a transformation.
a is the stretch of the graph, right?
Yeah, love it, right? It's an outside multiplication, so it's just going to be the vertical stretch, if you will. right? And to be clear, let's just do a quick graph right here of what we've got so far, which is x plus 3 times x cubed times x minus 2. If we do this, we see that, wait, this is like way too
Large.
vertical, right? Way too kind of,
And it's too high up.
yeah, so if we zoom out, oh my god, right? We see that it goes
Whoa.
way too low and way too high relative to what we're looking at here. So there's got to be some vertical kind of compression, okay?
Oh, and since
So,
Yeah, keep going.
so the first thing that you would probably look at is, or at least that I looked at, was like one of like -3, -4, just because that was a point that we had.
Right, so that's on the original function.
Right, on the
Okay.
original function. And I plugged that in, and what I found was because one of the x-intercepts is x plus 3, adding -3, or substituting -3 for x doesn't really help because then you get a 0, so you don't actually ever end up with a.
Right.
So we needed a point that wasn't an x-intercept, or that we didn't turn into an x-intercept, in order to start solving.
Love it. So we need a point that isn't an x-intercept to solve for a. So what did you use, Caitlin?
So I used, one second, where'd it go? -5.5,
So 1.5, negative 5.5?
negative 5.
Okay.
There it is.
So did you substitute this into this equation?
With the -4.
Ah, with the -4. Okay. So it seems like what Caitlin then did is took this function right here.
about -1.5, -5.5, that doesn't look exactly on.
You're right. It's an estimate. But Caitlin took this and then subtracted 4 to bring the function back down to its original, right, to where it originally is, right? Basically took all of these y-intercepts and x-intercepts and just shifted them down by 4, okay? So even if we look at that on this graph, on Grapher, we see that we're closer, but we need to change the vertical stretch, okay? So then Caitlin utilizes this estimate for a point, which is 1.5 and -5.5, and simply substitute it in. 5.5 equals a times, no, 1.5, right? 1.5 plus 3 times 1.5 cubed times 1.5 minus 2 minus 4, and then solve for a. Is that correct?
Yep.
Solve for a, which we're not going to take the time to do right now, but a equals
0.19753.
0.19753, which is awful close to 0.2,
Rounding.
which
The same as multiplying by 5.
which is the same thing as multiplying by 1/5.
That was impressive.
Yeah, that one, they'll never see what that was.
Mystery.
My students will never figure out what I meant.
Okay, so 1.5, so our final function should be, we substituted for a, what, 1/5, is that what we said?
Mhm.
That's a good question. Why not just rewrite it? 1/5 times this. We'll make the whole thing blue because we can. Maybe purple even, because I like that color more.
Whoa.
Are we done?
Me too.
And now let's bring in the original 1/5 times x minus 2 times x cubed times x plus 3 minus 4.
Are we done? Oh my god.
Okay.
Thank you, class.
So,
You are my Jesus.
are there questions? Are there questions? Are there questions? Please, questions. Miranda Fall first.
At any multiple 0 point,
Yes.
how would you know if it's triple 0 as opposed to like a quintuple 0 or like a I'm not sure which way it would work, but like a 6 tuple 0.
A great question. So it's interesting. So I can partially answer that question quite easily, right? I would say if it so we're talking about multiple zeros now. Multiple zeros. Okay. Talking about multiple zeros. So so you're basically saying, what's the difference? How do I know if a 0 looks like this? How do I have a sense for like the n at that 0, the power at that 0?
If like it would produce the same general.
Right. Is n going to equal 3? Is it going to equal 5? Is it going to equal 9? Wait, I heard that from somebody though. No, who said that?
Negative.
It's got to be odd. It's got to be odd because if it's even, ooh, besides 1. God, dude, I can't even keep up with you. Yes, it's got to be odd because if it's even, if n is 2, 4, 6, right? If it's even, it's definitely going to behave like it's going to make a parabola at that 0. And indeed, here you can't really distinguish between 3, 5, and 9.
Especially because if you plug in any of those in your equation, you're just it takes the same form.
Right. My guess is it will assume a similar shape.
Yeah, it's going to assume a really similar shape. It's basically just going to have to change the vertical shift because it just gets way
Well put.
way
Well put.
taller.
See, same shape at this point, but as Phoebe is pointing out, you'll just have to change the shift because you're taking x to the 5th.
It's the same function.
The same shape.
Equal.
The same shape. Not a purely equal function. You could scale it by a different
The
a.
shape would be the same.
Right. You can't be. Yeah.
Scale.
Right. Maybe you can make this 1 over a bigger number, like 100. Well, that flattens it too much. How about 1 over 30? Too much still. 10. Closer. 7. Now I give up. Okay. You guys get the idea. Let me go back to. Okay. And it can't be 1 because whenever n equals 1, it's just passing through. Linear. It's linear.
Like negative powers.
That's a great question.
Can you have negative zeros?
Is it a polynomial if your n is
No.
negative? Right. So it's not a polynomial.
You're never going to have these two shapes.
Because it's just what a polynomial is. We are going to deal with some negative exponents here shortly. So hold that thought. So Miranda, did we answer your question?
Yes.
Good. Nicholas had another one, and then Joe.
It was the same as mine.
Marvelous. Joe.
Do we not care that it's not really exactly 1/5? Is that just sort of?
It actually is. If you put the estimate of 0.1975, I bet you the graph doesn't change at all. Right. So you can use your approximate amount, or it made sense in this case because the original was 1/5. Just express it as 1/5. Same thing. Either way.
Like on a quiz, that would be fine. Okay.
Oh yes, yeah. And furthermore, on the quiz, if it were me and I were trying to cover my own rear end, I would probably leave it in the decimal. Okay. Other questions?
Wait, what? Isn't that what you just said not to do?
No, he said it's okay in this case because